Hey guys, welcome back to another problem solving tutorial, and in this tutorial I'm going to be solving the first hard problem in this series, and it's the largest rectangle in histogram. So this is a pretty tricky problem, but once you understand how the mechanics of the solution work, it's pretty simple actually. So I'm just going to be talking about how you might be able to find the solution, because okay, so it's basically asking us to find the largest rectangle within this histogram, so like the name suggests. But yeah, so some initial approaches we might have are, we might try and find every possible rectangle. So to do that, we just go on each bar and just see how far we could go, such as 2. Well, we can't really make any more rectangles because the next bar is 1. You can't make a rectangle into that, so the biggest rectangle we make in this 2 is from just this 2 alone. Then with 1, well, you might say we could go all the way across onto the left and right, so the biggest rectangle is going to be a 6 by 1 block. 5, you could do 5 and then go into 6, so you'd get this 2 by 5 block, and 6 you'd only get the 6, and then 2, well, again you could go 2 to the left and then 1 to the right, so you'd get a 2 by 4, and for 3 you wouldn't be able to go anywhere, so the biggest rectangle is a 3 by 1. So one thing you notice is we're basically just finding the largest possible rectangle area for each block. And one thing you need to notice is that if you have a block, so let's just say there's 2 over here, so the largest rectangle is obviously going to be the rectangle which has a height of 2, because if it has a height less than 2 and it's within this, then you could obviously go higher, and if it's more than 2, then this 2 isn't going to be able to fit in it, is it? So that's one thing. And the other thing you need to realize is, for the 2, if we only go to left by 1, it's pretty clear we can go another one, so we need to make sure we're maximizing this by going to the furthest possible left. And the way we find what the furthest possible left is or right, is we just look for the previous or next smaller element, because if it's smaller, that's going to end the rectangle right there. So basically looking for the largest rectangle which has this as a limiting factor, if that makes sense. Okay, so for each bar we're going to find the largest possible rectangle, and the first step is simply to create a map of the next smallest element and the previous smallest element for each bar. And this is actually a stack problem. I've covered this previously on daily temperatures, and there's also dedicated problems for next greatest, and I think previous greatest as well, but this time we're looking for smallest, but it should be pretty similar. So let's just write, we want to generate an array of we can actually just get the distance for it, since that will probably be more useful. So generate an array of distance to next / previous smaller elements. So let's get an example. For example, in this array, so the next smallest is going to be, well, for 2, the distance to that is going to be 1. Actually, I think it'll be more useful if we do distance, such as 1 is going to be fine. Yeah, so the distance to 2 to get next smallest is 1. For 1, well, there's nothing, so we might as well just say -1, which just means there is no next smaller. For 5, it's going to be 2, so that's going to be 2. 6 still is going to just be 2, and for 2 itself there is no next smaller, and the same for 3. So this is what we're expecting next smaller to be for this example. And for previous smaller, well, for 2 obviously there can't be anything behind it, so that's -1. 1 again is -1 because there's no element behind it which is smaller. 5, the distance is only 1. For 6, distance is again 1. For 2, the distance is going to be 1, 2, 3 to get to 1, and then for 3 it's just going to be 1 again. So this is what we expect for previous smaller. Now it's actually fairly easy to implement something which does this in O of n time. So hopefully it makes more sense if I show it to you guys in code. So we're basically just trying to, we're going to make previous smaller first, and I've already talked about this, but yeah, let me just do a stack implementation. So our stack is going to contain a number and the index because we're trying to get the distance to the previous smaller element. So yeah, let me actually create this array first. Previous smaller elements, it's equal to new array heights.length.fill -1 as the default. Okay, and yeah, let's just loop through this list. Okay, so the way this works is it's basically based on candidates. So we want to keep the best candidate on the top of a stack. So the best candidate is going to be the lowest, and it's going to be the most recent. And yeah, and then if we run into an element which is larger, then we're just going to, which is smaller than the top item on the stack, then we're just going to cut back until we either delete the whole stack or we find an item which is greater than it. So while stack.length is greater than 0, and let's say stack.length. Oh. So basically we want to cut back on the stack while number is a better candidate. So while num is smaller than the top item on the stack. Okay, we'll just pop. Basically what this is doing is, let's say our stack looked like this. Let's say it had, let's say it was 5, 4, and 3. Okay, so if we get a current number 2, or actually no, let's say we get a current number 3. Okay, so let's get 2. Okay, so if we have a current number 2, well, 2 is a better candidate than all of these because it's more recent. So it's going to be more likely to be the previous, and it's smaller. So it's better than 3, it's better than 4, and it's better than 5. Sorry, this is in the wrong order. This is going to be monotonically increasing. So yeah, it's a better candidate than 3, so it cuts that, but it's not a better candidate than 1. So it leaves that there. That's what this is doing, it's just cutting back. Now you'll notice, if there's still an item left in the stack, so if stack.length is greater than 0, then the previous smaller element is going to be this. So once previous smaller element is equal to stack, the top item on the stack. And then from here we just calculate the distance fairly easily. Distance equals I minus this dot index, and then we just set this like so. Fairly simple. So let's see if we're doing well so far. Let's just console.log the previous small elements, and I'll use this example, largest rectangle area. Let's use this. Okay, and so something seems to be wrong. Oh, of course, we need to add the item to the stack at the end. Okay, so let's just do stack.push, and we'll just have num index I, like so. Okay, see if it matches up. So previous smaller, we get, okay, yeah, so we get the right thing. Now the next thing is to implement the next smaller. So this works a bit differently. This is based off of signing off rather than just being a candidate. So I'm going to create another stack. The reason I used a bad naming convention is because I'm actually going to put both these loops in one once I've shown you guys how this works. But again, let me just loop through. Okay, so the way you calculate the next smaller, well, this is actually based on candidates. So we're adding in items to the stack, and for each item we're basically seeing how many items, like behind we can go to get the next item smaller. So for example, if the current item, right, we're just going to see in the stack if there's any items which this current item can sign off. So we'll just do while stack.length is greater than 0 and num is smaller than the top item on stack, then we want to sign off the top item of the stack. So sign off num is going to be stack.pop. The distance, remember this is a number behind the current number, so the distance is still going to be I minus sign off num dot index, and now we're just going to do next smaller. Oh, let me make this array as well. And yeah, the difference is basically instead of saying the current item's next smaller element, we're going to set the sign off numbers at that index. So this is equal to distance. And yeah, once we've done that, this number has signed off all of the ones it can possibly sign off. And if once it finishes, we know that the item which is left in the stack, well, that's obviously going to have to be smaller than number, right? So yep, and now let's just finally we just add this to the stack. So push, oh, I just realized I need to replace all of these with stack 2. Okay, and yeah, I'll just put this line in. Okay, so let's see how our next smaller is looking. Next smaller elements. Okay, now something is not working like it should. Huh. Okay, let's do a bit of debugging. Let's see the stat. Alright. So it appears, oh, I know the issue. We're pushing to the wrong stack. Okay. Okay, this is better. So we've got 1, -1, 2, 1. And yeah, okay, that's good. So we've managed to implement both of these functions in O of n time. The next smaller element for each element in this item in the height, and a previous smaller as well. Final thing I'm going to do before moving on is just combine these both into one. So I've got my stacks. I'm going to move this over here. So this, I'm just going to dedicate all of this to previous smaller, and then we'll just have next smaller code over here, and we can just put this over there. So you can see how this works, right? It's just in parallel because these are completely different stacks, so all the processing is done on different stacks and it's just inside the same loop. Okay, there we go. Now that we have this, all we have to do is just for each item we need to see the previous smaller and next smaller, and we can work out the rectangle from there. So for const I num of height dot entries, and yeah, I'm just gonna print out what it looks like for now. Console log num, let's say next smaller elements I and previous smaller elements I. Okay, so for 2 we have the next smaller is 1, previous smaller doesn't exist obviously. For yeah, and let's see for this second 2. So for second 2, the next smaller doesn't exist, but the previous smaller was 1, which is 3 away. So for the width, we're basically looking for, let me find an example which has both, which aren't -1. Okay, so 5, so the previous smaller, next smaller is 2 away, previous smaller is 1 away, so the width of this, well, the width of this rectangle is going to be this, so 2 plus 1 minus 1 because this all extends over here and next all the way extends over here, if that makes sense, you know, just trying to get rid of a parity. And yeah, same thing for 6, so this plus this minus 1, so the width of the maximum rectangle for 6 is going to be 2. So here's the ideal code. We want to get the width of the rectangle is going to be next smaller plus previous smaller minus 1. That's ideal, but you can see some of them are minus 1. So what we need to do is we need to actually fix that, and like for example, this 2 is for the previous smaller, it's minus 1, and obviously we don't want that. So if it's minus 1, we're just going to say const previous smaller distance equals previous smaller elements I is not equal to minus 1. We're just going to set it to this, and otherwise well, let's just think about this. The previous smaller we can assume is going to be to the left, and that is going to be the index plus 1. Okay, there we go. And I'll see the same kind of thing for next smaller distance equals, so again, let me take this, check if it's not equal to minus 1. If so, then we'll just give it that, and otherwise, well, for 3 over here, we can assume the next smaller one is going to be 1 away. So what's that going to be? Well, in terms of I, it's just going to be, yeah, it's going to be the length of height minus I, like so. Okay, and now let's see how this works. So let's just print the width for each number. So for 2 the width is 1, for 1 the width is 6, for 5 width is 2, 6 width is 1, 2 the width is 4, and 3 the width is 1. And again, I'm just talking about the largest possible rectangle within this area. Okay, and now from here, like I said earlier, it's pretty easy to get the height, because the height is just going to be the limiting factor of this number, which is just simply going to be the number itself. And finally we get area of rectangle, so of course just width times height. There we go. And now all that's left to do, this is an O of n solution, so all we're going to do, we're just going to set max area, and I'll just set that. I can actually start it with negative infinity, or I could just start it with height 0, doesn't really matter, let me just make sure. Yeah, so if area is greater than max area, then set max area to this. Finally we'll just return max area. Okay, there we go. So I know the way I explained the solution was a bit confusing, but hopefully you guys can understand. Basically for each element we're just finding a maximum rectangle which can be made including this element, and to do that you need to find the previous and next smaller elements to give the bounds, and from there we just compare all areas of these maximum rectangles and return the largest one. So like this example, we get 10, and that is the correct answer. So I'm just going to show you guys that this in fact does work. And there we go. So this was pretty bad. Runtime was pretty bad, although probably likely due to just a lot of variables, and also I believe I could try and squeeze it all into one loop, but optimization comes later. This was just the main idea of the solution. So you can see it took me quite a while to get this one, and I'm pretty sure I had to look at the solution, but you know, once you get it, it's good. So thanks for watching, and I'll see you guys in a future tutorial. Bye.